Now that movement of these hydrocarbon molecules through the nanopores, that's the major focus of our research. I study very, very small pores. They are at the nanoscale, and we call them nanopores. And these are the very tiny pores that we have detected in shale gas and tidal reservoirs. And we learned that actually fluid flow through this type of very small pores is different from fluid flow through the larger pores in conventional reservoirs. And that knowledge and the difference actually opens a huge research area for us that we were heavily involved in that in the past 12 years. One, we have a shale gas that the majority will produce natural gas. And basically the cost per certain amount of gas dropped a lot. So they shifted to oil to see whether they can use this technology to produce oil from these tight oils. They try it, and at the beginning they spent lots of money to do the trials, but they found that it works actually. When you're talking about a liquid flow through these nanopores, it's different from gas flow through the nanopores. The reservoirs that we are talking, they're buried deep in the ground. So the pores there, they're very small, but still there is enough porosity that they can fill and contain hydrocarbons in it. At the beginning, actually, we didn't know that there are any nanopore in this system because we cannot see them with the regular tools that we use to study rock samples. We are very fortunate that we have probably the largest collection of core samples. We have most likely the largest collection in the United States and maybe in the world. These nanopores, they are not everywhere on the sample, they are on certain locations. So the technique that I used was atomic force microscope, or AFM. The area that we scan at each time is very small, so we had to scan many areas until we find nanopores. The reason that imaging from AFM it give us the confidence, because with the AFM we are not emitting anything on the surface, we are not even touching the surface. In order to be able to see something at the nano scale, we need a very flat surface. Now, in order to create that flat surface, we use different techniques. We use ultramicrotome. These are extremely sharp knife. We started with that. Then we used argon ion milling, which is a more advanced technique to make a very flat surface. That's a flat surface that I can put under the AFM, and then by scanning that very smooth surface, I can detect the nanopores there. Once we detected these nanopores, then the question was, can we use our available conventional flow equations for a system that is mostly nanopores? And there is a famous equation, it is called Darcy equation. When it comes to a system that has nanopores in it, that Darcy equation is not valid. In order to be able to produce from any reservoir, you need to have a pressure difference. The pressure in the wellbore is low, the pressure in the reservoir is high. That pressure difference pushes the liquid or the gas coming towards the well, and then we produce it. Now, that Darcy equation relates flow to that pressure difference. And the permeability is the conductivity of the rock to let the fluid flow. The larger the size of the pores in a rock, usually, the larger the permeability. When you have nanopores, that permeability is going to be extremely low. So that permeability becomes, in terms of a more scientific way, becomes variable. And when permeability becomes variable, our equations become nonlinear. Now, that movement of these hydrocarbon molecules through the nanopores, that's the major focus of our research. That learning that we can produce from a system with nanopores Now we can produce more than 5 or 6 million barrels of oil from these tight oil reservoirs that we didn't have them 6 years ago. The recovery right now from tight oil is very low. The more knowledge we gain, the more we understand how these fluid molecules behave at that nano system, the better we can design techniques to improve that recovery. Currently, we have thousands of wells there, but we cannot produce from them. If someday these studies that we do, we reach to a certain point that we can extract another 10% of the remaining oil there, that's huge. That means that we can produce another 5-6 million barrels per day for another 5 or 6 years. The knowledge that we learn about the nanosystems in shale gas and tighter reservoirs help us to improve designs and help us to lower the cost per barrel dramatically. Also, it helps us to save the usage of water and environmental impacts are diminished. The projection is to learn more, to understand more, and improve the process. And I'm very optimistic about that.